Welcome back to the Thermo podcast. I'm your host, Jayton Miller, and today I have on the podcast once again Mr. Jay Feldman. Jay is always a pleasure to have on the podcast. Today we go into the deep depths of CO2 and why CO2 is actually beneficial for the body, why we want to produce more CO2, and why getting rid of CO2 may not actually be a good idea. So super excited to be able to dive into this one. So let's get into it. Jay, how you doing today?
I'm great, Jayton. Thanks for having me.
Yes, sir. So do you kind of mind just going over your background really quickly for the listeners who might not know who you are at this point?
Yeah, absolutely. So I dove into health, or started, I guess, becoming interested in health and fitness. It was more on the fitness side and more based on aesthetics and trying to perform well in the gym and get good results with the effort that I was putting in. And fell, I would listen to what I was being told to do, and I was always really diligent and very committed. And at the time, I was told if you want to see your abs and lose any amount of body fat, you just have to cut down on the calories, just the calories in, calories out. And that kind of started off the whole health journey of finding a lot of things that didn't work so well, and um, continuing to work really hard, and whether it was in the gym or with my nutrition, and always feeling like I wasn't getting the results that I should have been, or that there was something I was missing. There were pieces that weren't fitting because I was seeing other people who were experiencing what I was trying to get to, and it wasn't happening for me. Not that it wasn't at all, but it was just not as much. And one thing that really flipped that on its head, I was eventually a few years down the road, I was trying to really put on some muscle, and I was looking up some bodybuilding diets, and they were all eating like 3 times as much as I was, and they were all really lean and ripped, and so I realized that there was at least something that was not right from what I was doing. And at least that started setting things off in a better direction. And but that set off kind of this interest in health and nutrition. And so I went on to find paleo and low carb. And at the same time that those things were going on, I was, with this passion, I knew I wanted to help other people become healthy. And so I began at university. I was pre-med, studying neuroscience and exercise physiology. And the plan was to kind of go down that route, and over time became a little disenchanted with that system, and started to get the feeling that it wasn't really the best way to really help people restore health, and tended to more just manage symptoms and keep people in the states they were in at best, and normally at worst would make things worse. And so that led me on a path of continuing to try new things and figure out the best way to help people reverse various symptoms and conditions. And after a while, came across the bioenergetic view of health, and things kind of blossomed from there. And now that's what I do. I'm a health coach and researcher, and I help people deal with all sorts of issues and conditions, things like autoimmune issues, and helping with weight loss, and kind of everything from there, all sorts of chronic health issues, and gut issues, and everything. Yeah.
Mm-hmm. You have a pretty awesome podcast as well.
Oh yeah, thanks. Yeah,
Mm-hmm.
the Energy Balance podcast.
Yeah. So did you ever, whenever you first came across the bioenergetic view, did you have some initial resistance to it?
Definitely. And it was a long transition as well, where so on one hand, there's some resistance. On the other hand, I was very much looking for an out from the low carb, the fasting, the keto, which I wasn't enjoying. I was always hungry. I was always very obsessed and focused on food. I didn't have the energy that I wanted. It didn't, it was very much in that mindset of fighting against your body, right? Where everything that you're doing is trying to kind of hack things, or trying to fight against the cravings and hunger for the things that you want. All those carbohydrates that your body wants, those are really the most harmful thing. And or even just food in general, right? That's why we're fasting, which I was not enjoying. And so when I came across these alternative ideas, it definitely took quite a few times of exposure before I even kind of looked into it further. But then as I did, it was really great to put the pieces, to hear some of those things, and some of it had resonated with what I was experiencing. And so I was already kind of tending to increase carbs a little bit on workout days, for example, because I knew I felt better when I did that. And so this kind of gave me a bit of a green light on that front. But it was still a long time of doing kind of like a higher carb paleo approach, before, and various iterations of that before kind of really diving in and shifting more toward sugars and fructose, which, I mean, there's a long time I was still higher carb, but monitoring my fructose intake because that was like a major concern of mine. I was still stuck in that dogmatic mindset that fructose is a poison. I'll thank Dr. Lustig for that and others. And yeah, so there was some resistance there for sure, but the bigger picture there was so different from anything else. There was such a cohesion and such a clear in a way that I didn't understand yet, but I knew that there was this different picture of looking at health that nobody else was really looking at it through that same lens. No one else was had this cohesion to it where everything was so directly integrated and made so much sense. And so that was something that was so desirable to me, was to understand that. And so that was so it was a bit of a tiptoe in, but there was a lot of excitement along the way and a lot of mistakes too. But yeah, I don't know if that answered your question. But.
Yeah, definitely, for sure. I have one more question, and then we can dive into the main topic of this podcast, because I'm starting to go off on a different kind of rabbit hole here. But so if you could explain kind of the bioenergetic theory in 60 seconds, how would you explain that? I'm kind of curious as to what your definition of it would be.
Yeah, I always resort back to the idea that the bioenergetic view is a lens of looking at health that centers around energy as the fundamental feature of our health. And so I think that's kind of, in a sentence, that's what it is. And what that means is that when we're considering any disease process, any symptom, any type of food, any supplement, we're able to consider how those things affect us on that fundamental energetic level. And that will help to inform whether this thing is something that's going to be supportive to our health or not. And we see that branch out into every mechanism, into every reductionistic pathway, everything else. It all follows suit with what's going on energetically.
Awesome. Heck yeah. And so one of the beneficial side effects of the bioenergetic approach is increased CO2 production. So can you kind of go into the importance of that and kind of how that happens?
Yeah, it's funny talking about carbon dioxide and me. When I found the bioenergetic view, Danny Roddy had a video talking about carbon dioxide, and I think it was critiquing Dave Asprey at the time, or keto diet. He was talking about Dave Asprey, and this was before this was one of those introductions to it that I just put off and maybe didn't circle back to for a little while later. But I mean, carbon dioxide is not talked about virtually anywhere outside of the bioenergetic community, or maybe particular people who are concerned about respiration for some reason, certain disease processes. But it's a really helpful indicator of what's going on metabolically. And the reason for that is because, perhaps counterintuitively, carbon dioxide is the driving factor of oxygenation. So we all know that oxygen is very important to our bodies. That's the whole reason, well, at least a main reason why we breathe, is that we need to take in this oxygen from the atmosphere. And a lot of people aren't even really all that aware of what happens after that. But essentially, it needs to get into our cells. And when it's in our cells, it helps our cells produce energy. And so that oxygen is a fundamental feature of life. We know that if we can't breathe, we can't live. And because of that, there's this idea that we need to be focused on oxygen, that if we get enough oxygen, then we can use that oxygen well. But we don't find that to be the case at all. Instead, carbon dioxide is the main factor that allows us to use oxygen. And so, of course, we need to have some amount of oxygen there. But if we don't have enough CO2 or carbon dioxide, we can't use it. And so there's all sorts of factors that will affect how much carbon dioxide we have. And there's all these different places where carbon dioxide helps us use oxygen. But that is the most fundamental factors, that it does help us use oxygen, and it has all sorts of other benefits too.
So whenever they're measuring like the metabolic rate with the rate of oxygen consumption, is that typically going to be synonymous with high amounts of CO2 in the system as well?
Typically, yeah. Yeah.
Okay.
Yeah, because what you're looking at there is typically that conversion from oxygen to CO2. So in that way, it tends to be the best indication of metabolic rate. Yeah.
Okay. And so like, what's actually happening? So in the lungs, whenever you're transferring those two, why is carbon dioxide necessary for like the transport of oxygen? And then like what's exactly happening in the cell whenever there are high amounts of CO2 versus a low CO2 environment?
Yeah, so that brings us to what are called the Bohr and Haldane effects, which are kind of the same effect, just in different places, and they're kind of opposite, but yeah, they're just identified by two different people. So the Haldane effect is what goes on at the lungs. So that was the first thing that you asked, and basically we have the main um, compound that allows us to transport oxygen is called hemoglobin. It's in our red blood cells, and that's what we need to pick up oxygen at the lungs and then deliver it to our cells. And that hemoglobin also will carry carbon dioxide. And so in order for us to pick up oxygen at the lungs when we breathe in the air, that hemoglobin needs to have carbon dioxide attached and exchange it for oxygen. So that's the first part, and that's called the Haldane effect, is that when the hemoglobin is bound with CO2 and it's at the lungs, it's able to exchange that for oxygen and then enter into the bloodstream. Those red blood cells go through the blood, through the pulmonary. At that point, it's the vein that's going into the heart, and then that goes on to the rest of the circulation. And so then that hemoglobin will eventually reach some cell that needs some oxygen, and at that point, the hemoglobin is carrying the oxygen. And if the cell is respiring well, if it's producing energy, which we talk about that as mitochondrial respiration, and the reason is because, like, the reason why we call it respiration is because of this exchange of oxygen and CO2 that's going on when we're producing energy. And so if the cell is producing a lot of energy, it'll be producing a lot of CO2, and it will release that CO2, and that CO2 at the cell will be exchanged for the oxygen from the hemoglobin. So the hemoglobin picks up the CO2 and drops off the oxygen for the cell to use, and that's called the Bohr effect. So that's like the two kind of most surface level areas where we're seeing the interplay between carbon dioxide and oxygen.
So at the cellular level, what's kind of happening in a high CO2 environment versus like a low CO2 environment? So like how would a cell be unhealthy without high levels of CO2?
Yeah, so that is when I was talking earlier about people not talking about CO2 generally when they're talking about health, and part of the reason, especially that's not the case in the low carb spheres, because in that case, you would have to argue that you want to have low CO2 because carbon dioxide is produced at a few different points during energy production. And some of the features of energy production are shared between fat metabolism and carb metabolism, but then there are certain pieces that are not, that are just going on in carb metabolism and just going on in fat metabolism. And so when we're producing energy from carbs, there's an extra step earlier on that leads to extra CO2 production. So basically, anytime we're respiring, whether we're using fats or carbs, we're going to be producing some amount of CO2. So anytime we're producing energy, we're producing some amount of CO2. If we're producing energy from carbs, we'll end up producing around 50% more CO2 per revolution through energy production. The reason why that's important is because carbs also tend to be oxidized faster. We burn them faster. So you probably end up producing more than 50% more CO2 with carb metabolism versus fat metabolism. Well, let's say at least 50%. And yeah, so that's the main process. Is a lot of people say carbon dioxide is just a byproduct of metabolism. It's a byproduct of producing energy, but in reality, it's one of the most integral pieces that allows us to continue producing energy. And maybe later on, we'll talk about these different scenarios where when you don't have enough CO2, you can't produce energy very well. It causes a lot of problems. So it's part of this feed forward loop. We've got a lot of these positive feedback signals that basically are saying things are going well. We're producing energy well. We're using this fuel we're taking in. Let's keep doing it. We're in a good place. And carbon dioxide is one of those signals that we're producing a lot of it at the cells. If we're not, and we're not producing a lot of carbon dioxide, we end up producing a lot of lactate. It's kind of like the low metabolism version of carbon dioxide. And that signals the opposite. That is all these different downstream effects that tell our bodies to slow down their metabolism. So that's another reason why carbon dioxide is so important, is just as because it is one of these main indicators, these main signals of high metabolism going on in the cell.
Sounds good. Do you mind diving into some of those things, some of those negative effects
of lactate?
Mm-hmm.
Yeah. So I think it's I don't know if I've heard it phrased this way, but I like to think of lactate as the low metabolism version of CO2. And the reason for that is because it does everything CO2 does, but worse. So when we're not producing, basically there's this diversion. When we start with glucose, which is our main carbohydrate that we would be oxidizing in the cell for to produce energy in the mitochondria, it can either go all the way down to produce energy all the way through glycolysis, through the Krebs cycle, and through the electron transport chain. You end up with all this ATP at the end. Or if there's something blocking any part of that process, especially later on, which is normally where things are blocked down farther in the deeper parts of respiration. And this can be blocked by anything that we're eating, anything that we're doing that's really stressful, whether we're eating a lot of PUFA or really hard to digest foods that are causing a lot of endotoxin production. Those things end up affecting us on this energy producing level, or if we're not getting enough nutrients, whatever it is. And so when that happens, if there's any blocks there, the glucose can't end up making it all the way to the end to produce energy, to produce a lot of ATP. And it gets basically stopped before the Krebs cycle just during glycolysis. And when that happens, instead of basically pyruvate is the end product of glycolysis that then needs to be converted to acetyl-CoA to get to the next step of the Krebs cycle. And that step, which is performed by pyruvate dehydrogenase, that's the enzyme, is the one that is kind of the flip, the switch that gets flipped between whether you have good glucose metabolism or glycolysis, just people call it aerobic or anaerobic glycolysis, depending on the context. And so when the pyruvate does not get converted down to acetyl-CoA because things are getting blocked up, normally that involves a bunch of other signals that force it to be directed to lactate instead of acetyl-CoA. And the process kind of stops there. It's not able to continue going on to produce energy. You're just stuck between pyruvate and lactate. And that's done by lactate dehydrogenase. So when that happens, it's already a sign of a problem. It's already a sign that the cell is not, or the mitochondria in this case, is not able to produce a lot of energy from glucose. There's something going on, and that itself is an issue. But there's some value in getting that lactate production, because you get some amount of energy during that process from glucose to lactate, and you're able to, in the short term, you're able to kind of rescue the cellular state, because one of the signals of poor metabolism at that time is a low NAD to NADH ratio. And in the short term, converting the pyruvate to lactate helps to restore that. It converts NADH to NAD. So you start to restore that ratio a little bit, and it's kind of like a backup release valve. And that can be great for a short-term situation, but we don't want it to be happening in general, like in a chronic way or in a long-term way, or outside of intense exercise, for example. And so when it does that, we end up with this buildup of lactate, and the lactate just leaves the cell as the kind of end product there when you're producing a lot of, when the glucose is going through the lactate. And interestingly, just like CO2, the lactate can bind with hemoglobin and lead to the offloading of oxygen, just kind of, like one of those backup ways to oxygenate the cell. So, but then when you have the hemoglobin bind with lactate, that then has to go back to the lungs, where you have to pick up the oxygen again. Normally the hemoglobin picks up the CO2 from the cells, goes back to the lungs and exchanges it for oxygen. But when the hemoglobin is bound with lactate and then goes to the lungs, it's then having to drop off lactate in exchange for the oxygen. But the problem there is that when we're getting rid of the CO2 and picking up the oxygen at the lungs, we breathe off the CO2. It just exits in the air. But lactate can't do that. We can't breathe off lactate. So it ends up accumulating at the lungs. And when you have this, part of what allows for the exchange at the lungs is that you're supposed to have a low concentration of CO2, high concentration of oxygen. So you've got this easy gradient. It's easy for the hemoglobin to pick up all this extra oxygen that's kind of forcing its way in. But with lactate, if you start to have this big buildup of lactate, you don't have as strong of a concentration gradient there. And so it's much harder to pick up oxygen at the lungs because the lactate's not able to be released like the carbon dioxide. So you end up with so that's just one example, basically, is that you're not able to pick up oxygen at the lungs as well when you're using lactate, or when lactate's being produced. And there's a few other kind of parallel processes that go on as far as the mineral balance of the cell that are also, part of, like, have a role here, where when the carbon dioxide is produced in the cell and leaves the cell, either with the hemoglobin, or in this case, when it doesn't leave with the hemoglobin, it tends to ionize and bind with sodium or bind with calcium and leave as sodium bicarbonate or calcium bicarbonate. And That's helpful for mineral balance. We don't want to have a lot of sodium and calcium in the cell. They cause a lot of swelling, and they tend to happen when the cell is uh, is in a lower energy state. It causes contraction and activity, which is great. You want that in the short term, but again, long term, you don't want that. Whereas lactate doesn't have that effect. It doesn't leave with the sodium or calcium, and instead it tends to leave it with the protons, like with the acidic components, and it leaves the cell in a more basic state. So that's, again, I know these are kind of like nitty gritty things, but just a few different areas where the lactate directly causes problems there. And there's, while this sounds all, this doesn't sound all that relevant, this is something we see in all sorts of chronic health conditions. Like when we know like producing lactate when we're sprinting or something is not a problem. We go into what's called oxygen debt. That lactate, after we're done sprinting, the lactate leaves our muscles, it goes to the liver, gets converted back to glucose, goes back to the muscles. And, you kind of went into debt that was then paid back by the liver, and you're good to go if everything's okay and you're generally healthy. But these are states where you're in this chronic lactate producing state. There are states where you're in this chronic lactate production. You're not producing a lot of energy, and you tend to be pretty sick when that's happening. You tend not to be feeling too well. It includes situations on the severe side, something like sepsis, which is like an extreme infection, normally when someone's like close to death. You also tend to see it in like, heart failure, or in traumatic brain injury or stroke and things like that. You see it in acute respiratory distress syndrome, excuse me, when like, if somebody has a really severe respiratory infection, maybe like COVID, for example, you'll see excess lactate at that point. You'll see it in any altitude sickness. You'll see it in a panic attack. All these states where you're seeing excess lactate and lack of CO2, and both of those things basically in conjunction act together to cause this stress. There's another feature too, for example, is that carbon dioxide helps to vasodilate our blood vessels. So it increases circulation and helps to bring the blood to the tissues that need them. Whereas lactate doesn't do that. Lactate won't lead to that vasodilation. It won't lead to that increased circulation. So you end up with constriction. And yeah.
So whenever it comes to vasodilation, can you kind of explain the differences between the benefits of CO2 for vasodilation versus nitric oxide?
Mm-hmm. Yeah, so I would say that nitric oxide tends to go in tandem with the lactate side of things. They both, like nitric oxide will allow for vasodilation in the same way that carbon dioxide does, but it tends to only do that under stress, and it tends to go with the low metabolism side. So when we were talking, or when I mentioned earlier about those things that block respiration, nitric oxide is one of them. It blocks one of the enzymes called the Krebs cycle called aconitase, and which will end up causing a buildup of citrate. And that citrate, this is actually something that's implicated in obesity and fat gain, because buildup of citrate then leaves and gets converted to back to acetyl CoA, malonyl CoA, and then fat. It's part of the fat production pathway. So nitric oxide is actually somewhat implicated in that process, and it also blocks things of the electron transport chain too. So that's just kind of some evidence that we see as far as how nitric oxide acts on that stress side. And again, this is great short term. If we're under stress, if we're, for example, sprinting, which will cause some stress, we want to be able to vasodilate without a lot of CO2 during those couple of minutes or 40 seconds or whatever it is. And so nitric oxide is great for that. But long term, it's not something we want to be relying on for vasodilation.
Okay, interesting. So do you know how CO2 tends to produce the vasodilatory effect?
So I don't know of the direct mechanism. I would assume so. What you see as far as the nitric oxide production is that when the cells of the blood vessels get stressed, they start to produce nitric oxide. And when I say stressed, I mean their energy production gets inhibited for some reason. They'll start to produce nitric oxide as that backup mechanism, and that will force kind of basically what. Okay, to back up. So vasodilation is when the blood vessel relaxes, right? So those cells all have to relax. Carbon dioxide has a general relaxing anti-swelling effect. It supports general structuring of water. It supports the energy producing pathways. And so I don't know if I've seen actual research on this. I'm trying to remember if I have or not, but I would assume that it just directly causes those blood vessel cells to relax by supporting their energy production. And that allows for the relaxation and the vasodilation. Nitric oxide tends to do that through it does it through an energy depletion mechanism. And generally, when we're seeing energy depletion, we see a contracted state. And I don't remember what the difference is. I know there's some, maybe I'll send you the study after, but there's some research looking at how nitric oxide induces that vasodilation, and it does it through some energy depleting mechanisms. I don't know exactly why that would lead to relaxation in that point, because again, normally we would expect contraction there. So yeah, I'd have to maybe go back and look. Maybe another thing that could be going on is generally when you have those stress factors, the initial thing that's caused is a ramp up of energy production. Anything that causes stress, and people know this, like if you use glucocorticoid or adrenaline, for example, that's a great example. Adrenaline is going to drive stress-induced metabolism very quickly and lead to a lot of energy production, and that'll cause short-term relaxation if it's working well. Long-term, it's an issue. And so maybe the nitric oxide works in that same way, but I don't remember the exact mechanism there.
So other than vasodilation, what are some of the other systemic benefits of CO2?
So the vasodilation is important, but it's kind of like a byproduct, right? Just a piece of that puzzle. But in general, when we have the CO2 being produced inside the cell, it does a couple of things. I know I mentioned that it helps to bring out sodium and calcium, which helps to reduce the concentration of those in the cell, which is helpful because those draw out water, just like regular bulk water. And so that can be helpful, especially in the context, we see that in swelling, for example. We know that edema and swelling is one of the main first features of stress and inflammation. And so if you get a cut, or if you get a mosquito bite, for example, and you itch it or anything like that, and it gets inflamed, it swells. And so we see that very clearly there as a situation where swelling comes about as this result of stress. And we see that a lot in certain chronic health conditions too, like diabetes. You'll be more susceptible to a lot of edema and swelling. And that's a state of, pretty severe energy failure or energy inhibition. And so swelling, those are places where we see it very clearly. It's also involved in things like heart failure and high blood pressure, because in those cases, speaking of a lack of vasodilation, when the lining of our blood vessels are swollen or our heart is swollen, for the lining of the blood vessels, they can't relax enough, so they stay constricted, and that causes high blood pressure. For the cell, it stays swollen and like waterlogged, and it can't relax either, so you can't get a full heartbeat. Basically, you can't relax enough to allow enough blood to flow in and then contract very well to let it come out. So we see this feature of swelling in all these different states, and you see it in basically, I know I alluded before to like situations of respiratory alkalosis, like altitude sickness or ARDS or these various chronic health conditions, and you see edema there too. You see in these conditions that are characterized by low CO2, you see swelling in the brain, cerebral edema. You see it in the lungs, called pulmonary edema, and this is going on even if you're not experiencing any of those particular situations. This is going on some smaller level when we're under stress and inflammation. And you can see it in your muscles, for example. If you use your muscles a lot and they're in recovery from some sort of damage or inflammation, they'll be harder. They might be a little swollen. Sometimes people will gain weight after they've worked out, and that can be the reason for that. And then it'll go away after a day. So that's one of the main things that happens when we're not producing energy well. And we see carbon dioxide as one of the most effective things to reverse that state. So there's a drug called acetazolamide, which is used anytime you're basically seeing swelling. It's used in altitude sickness. It's used in these situations where you see edema. It's used in like glaucoma and epilepsy as well. So you see it in all these states, and it's very effective at reducing swelling. And that's because what acetazolamide does is it increases the carbon dioxide. It decreases the conversion from carbon dioxide to bicarbonate. And so we see this direct anti-swelling effect, both because it helps to pull a couple things. It helps with the oxygenation, which encourages energy production, and that causes a lack of swelling because it structures the water in the cell. It helps to bring the sodium and calcium out, which also helps structure the water. And then it potentially has some direct effects in water structuring by interacting with the protein structure, has some withdrawing effects with the electrons, and then helps to structure the water directly. So I think that when we're talking on the fundamental side, there's very few things that are as fundamental as that. And then it does branch out to, again, virtually every other situation we can be in.
Mm-hmm. So Um, One of the things that I've seen with CO2, for instance, is like the story of the guy who snipped off the tip of his finger and then he encased it in the kind of bubble of CO2, and he was
Yeah,
able
yeah.
to like grow back the tip of his finger.
Mhm.
Um, do you know why it tends to have that kind of healing effect?
Yeah, so that I like that you brought that up. So healing and relaxation, I think, are the opposite of the swollen, contracted, low energy state. And so that is one thing that I think is worth mentioning is like the relaxation. So when someone's in a panic attack, or if they're hyperventilating for any reason, if you administer CO2 or have them bag breathe, a lot of times that'll cause relaxation. And that's because it's causing that relaxation on the cellular level. And they see that again. I didn't mention this earlier, but in those severe states where you see high lactic acid and low CO2, when you administer CO2, normally when they're concerned about respiration, they administer just 100% oxygen or just only oxygen. There's very, very rarely CO2, which there's quite a bit of research saying that might not be such a good idea and tends to make things worse. And if you add carbon dioxide to those states, it virtually reverses them. It completely increases the circulation, reduces the edema, just to pretty incredible degrees. So yeah, and then as far as healing goes, I think we're taught that the inflammation is part of that healing process. And I think in general, when we're healing through inflammation, it tends not to be real healing. It tends to be more of like band-aid cover-ups. So when you have inflammation and you then have the swelling that results, the next steps beyond those, the layers beyond those are fibrosis and calcification. And that's a lot of times, if we have like a scar, for example, that's basically what that is this kind of unorganized healing, this disorganized healing that was set off by inflammation and swelling and everything. And generally, that would be what would result, I guess, if you cut off the tip of your fingers, you would have basically some sort of scarring there. And we know that scarring it's not actually like healed, like healthy skin. It's kind of like just like a damaged like a way to stop up the the issue. It's like if you had a boat and you just patched it up. It's not actually like you replace the floorboard or whatever. If there's a hole in the bottom of the boat. So I would assume that as far as healing any tissue, carbon dioxide would really help to prevent that swelling, prevent that whole inflammation cycle, and allow for the actual regrowth of tissue, which we know is possible in the right states. We in all the places that we're told that it's not possible, they've found it to be possible. We were told that you can't regrow neurons, you can't regrow brain cells, and various other things. And there's administering something like progesterone tends to help encourage that, for example. And there's some interesting like bioelectrical research that they find that causing certain bioelectrical, I don't know if it's impedance or what it would be considered, but when they change that state, they see healing in various areas as well. And so I think carbon dioxide is just fits right in there and supporting the healing processes and the regenerative processes. And I know people talk a lot about beyond bag breathing. There's other things that you can do to increase your environmental CO2. People talk about CO2 baths or buteyko breathing, things like that. I think that those are all good healing strategies too.
Definitely. Yeah. I've experimented a little bit with like the dry ice.
Okay.
Um, that has definitely been an interesting experience. It's definitely tingling whenever you're kind of submerged in the fog.
Yeah.
Um, yeah, it's definitely interesting for sure. Um, so what are some ways that we can begin to increase our CO2 production?
Yeah. So, I mean, if we're sticking on that last tangent, I mean, probably well, I shouldn't say easiest way. It's not always that easy to acquire a carbon dioxide bath or something, but, and you want to be very careful, disclaimer, you don't want to be breathing in straight CO2. So you want to be careful when you're doing those things. But yeah, so increasing it environmentally is great. Using something like a CO2 bath, potentially doing some bag breathing, doing some buteyko breathing, or going to a high altitude location. Those are the best ways to do it environmentally. Some of those things anybody can do, like buteyko breathing, for example. Other ones can be a little tougher. But what goes on there is that basically these are various ways of increasing the carbon dioxide either in the air that we're breathing, well, basically in the air that we're breathing or through our skin or something. And that tends to improve our oxygenation, tends to actually slow down our breathing if we're healthy and responding properly. And that leads to less blowing off of CO2, which increases the CO2 retention, and it increases our usage of oxygen. So when you take high altitude, for example, there's this what they call a lactate paradox. And what it is that when you're at high altitude and you are exercising or doing some form of physical work, they find that you produce less lactate at the same level of exertion that you did compared to at sea level when you're not acclimated to altitude. And this is supposed to be paradoxical because normally what they say causes lactate production during exercise is a lack of oxygen. You can't get enough oxygen to the cells, and so you start with this anaerobic glycolysis. But they know that there's less oxygen circulating in the air at altitude. So it's like, why would you have less lactate? You should produce more lactate at altitude. But what it is that when you're acclimated, you're retaining CO2 much better. So you're able to oxygenate much more efficiently with less oxygen in the air. And that improves your metabolism to the point where you don't need to resort to the lactate production as quickly. And so you can mimic that same effect by practicing something like buteyko breathing and basically hypoventilation, working on slowing your breath, breathing very gently, breathing through your nose as opposed to through your mouth. But you can also do it by virtually everything that's going to support you metabolically, because the more we're running through energy production, and especially using carbohydrates for that, the more carbon dioxide we're going to be producing in our cells, the more relaxed we'll be. And again, kind of goes again with lowering our ventilation naturally and breathing off less CO2, which helps to increase CO2. And that's another thing that you see when generally when you see someone who's really old, they're kind of on their last legs and they're maybe in the hospital or something, you tend to see very labored breathing, a lot of quick, short breaths. It tends to be very difficult. That's a sign of what's going on when you're in that extreme stress state. And we basically want to encourage the opposite. So yeah, doing like direct environmental things to increase the CO2 retention is great. And then also doing the internal physiological things to support metabolism, support carbohydrate burning is also great. And so we can dig into that more too, because obviously there's a lot of pieces there. It's not always so simple.
Definitely. Yeah. I think one of the first ones that I'd kind of like to get your opinion on would be I've seen some studies showing that red light can increase CO2 production in some cases. Do you know why that would happen?
Yeah, so red light has some pretty cool effects just in that it's shown to directly create that structuring of water. I know I mentioned that earlier. Generally, when we're taught to think about energy, we're taught to just think about this bond in the ATP molecule. And when we break it, it releases all this energy that we can use for some sort of reaction. And instead, there's people like Gilbert Ling who have put forth these ideas that in reality, the way that our cells hold and use energy is through the structuring of water using the protein skeleton of the cell. And Gerald Pollack has built on that research and has investigated various substances that help to increase the structuring of water, and red light is one of them. And I want to say too, I think that our cells will actually produce their own red light too when they're producing energy well. But so when you're kind of exposing them to red light externally, it's kind of mimicking that same effect, and it's kind of a way of directly increasing that structure in the short term, which can help in the long term if it's fixing things. And then that tends to be why you see increases in healing and regeneration with red light as well as using external CO2. But yeah, I think it's a pretty direct effect. There's also some evidence that it activates part of the electron transport chain, some of the pieces there, the cytochrome oxidase in particular, to help increase energy production. And we talked about nitric oxide earlier. Nitric oxide binds in with cytochrome oxidase in a way that prevents it from producing energy. And red light can potentially help with the dissociation there, so that it's not being blocked anymore. But it seems to be that might be more of a secondary effect, I think, versus a more direct energy, like infusing effect, basically, of the red light.
Okay, interesting. So would the same thing be for sunlight?
Yeah. So sunlight has a good amount of red light, so it would definitely have some of that effect. There's a lot of other light too that you're getting with the sunlight, which can have a lot of other benefits, but I don't think those other wavelengths will have the same direct energies like contributing effect. directly, but I think that they'll have other benefits too. So yeah.
Sounds good. Um, so whenever it comes to different types of exercises, um, so for instance, like cardiovascular exercise is going to create a lot of CO2 giving off. Are there different types of exercises that you've come across that can help actually just increase the CO2 production and retention of it?
Like while somebody's doing cardiovascular exercise, or you mean instead of?
I guess both.
Okay.
Mhm.
So yeah, so generally our ventilation, like our breathing rate is the best way to is one of the quickest ways to manipulate our carbon dioxide retention. So if whatever exercise you're doing, or even just when you're not exercising, which for some people, for someone who's less healthy, not exercising is the same as exercising for someone who is healthy. So what I mean there is that ideally, as I mentioned earlier, we want to be breathing gently and slowly, and that will reduce the amount of CO2 we blow off and increase the retention of CO2 and help to oxygenate our cells and everything on from there. So when we're exercising, we want to be trying to do that as much as possible. So this is part of the reason why Ray Peat has said that you don't want to be doing any exercise that leads to mouth breathing, like where you can't sustain that exercise without resorting to mouth breathing, because it's an indication of stress and losing carbon dioxide. I don't fully agree. I think that if you're healthy, you should be able to go to that point and then come back without a problem. But that is a sign of stress. It is a sign of when you're losing carbon dioxide. So regardless of what exercise you're doing, if you're able to do it in a way where you're breathing through your nose and you're breathing relatively gently, then that's the best way to retain the carbon dioxide and minimize the stress from it. So I think that would be part one. And the point I was getting at earlier was that as far as for some people, just not doing anything is the same as somebody else exercising. For someone who's very fit physically and maybe in an endurance capacity, can maybe jog or run for a while still maintaining a very low breath rate and probably retaining a decent amount of CO2. And there's questions as to whether getting to that point doesn't come at a cost and all of that, but that's kind of beside the point. Where somebody else might struggle even when they're at rest to do that because they're struggling with the carbon dioxide production and oxygenation. So they have all these signals telling them that they need to hyperventilate even when they're just at rest. So there's just a bit of a contrast there, but in both cases, you want to be implementing the same concept, really. So that would be like during whatever exercise you're doing, that would be the most important thing. And something that can help with that might be, if this is extended exercise, is getting some sugar while you're exercising, whether it's like a little bit of juice that's maybe diluted, or even some Gatorade or something. I mean, I prefer not that just because of the added colors and like artificial coloring and things. But having some sugar while you're doing it is a good way to prevent the stress, continue on with the carbon dioxide production, and allow you to stay relaxed. So that'd be something to consider. As far as types of exercise that might be better, again, a lot of it's going to depend on the individual. Generally, for someone who is, walking or weightlifting or doing, I don't know. I mean, there's like, of course, lesser intensity things are going to lead to less of a need for the hyperventilation, less of a shift toward the lactic acid production because they don't require as much immediate energy. But again, I do really think that it's okay to do something like sprints that causes you to be out of breath for a bit, as long as you're coming back to relaxation very quickly and you're recovering really well and you're not having any extended inflammation. And a lot of sports or other activities, whether it's swimming or, well, swimming, you should, I mean, it depends how intensely you're swimming, I guess. Or hiking or playing soccer or tennis or some sort of martial arts, kickboxing, jujitsu. And a lot of those cases, the exercise can be too intense to where you do kind of lose the retention of CO2 and you might have to resort to the mouth breathing and some of the lactic acid metabolism. I still think there are a lot of benefits there that can outweigh those effects as long as you're healthy enough to recover very well from them.
Definitely. Yeah. I would say from someone who is very new to the jujitsu world, the psychological benefit is definitely a payoff that outweighs a little bit of the physiological effects for sure.
Yeah. And again, I think it's about finding a balance there. I think there are certain people where they'd probably be better off not going that route and not forcing all this intense exercise because they're really struggling in other areas of their health and it might be inhibiting them. Whereas I think other people might be totally fine with doing it a certain number of days or amount of time per week. But it's tough with those sorts of things where you aren't necessarily in control of what's going on. If you happen to be in a class where they're doing a lot of drills or something that's very intensive, you can't always just decline to do it. So there's a balance to be had there. And sometimes that's just a little tough in our modern society where like just the narrative is pushed, right? Whether you're working with a trainer in the gym or doing some sort of martial arts class. And, there's just this narrative that you just need to push it and do all this cardio, like, I don't know, endurance training and things, which I think can be like that's just kind of a waste, right? I mean, you're not getting a benefit by, I don't know, when they make you do like a million sit-ups and push-ups and I don't know, punch each other in the ribs. Like I say this is someone who used to do Muay Thai and would love to still do Muay Thai, but there's some things like that are just kind of dumb and I try to avoid.
Yeah, definitely understandable for sure. So if there is one thing that people could start doing right now to help increase their CO2 production, what would you say would be the one thing that you would tell them to do?
So I think so much of that is individual that the only thing that I think could be is the thing that I think is the most universal is probably the breathing, working on reducing your breathing, trying something like Buteyko breathing, which the basics are just breathing through your nose, breathing gently to the point where your breathing is basically inaudible. I think it's just very gentle. And that you're breathing in maybe about 95% or so of what you would naturally breathe in. And I would say that that's the quickest, easiest way. It's a practice that you can do on a regular basis, come back to it a few times a day, once a day, whatever it is, until it's kind of the norm. I think that's the best universal thing. But I think for someone who's dealing with a major gut issue, for example, addressing that gut issue is going to be way more important and get way more at the direct issue than the Buteyko breathing. But it's just hard because that's not a universal situation. But I think most people tend to have, people who are listening to this probably aren't eating a lot of PUFA, but for most people, PUFA is a big issue. Eating a lot of hard to digest foods might be a big issue. Still dealing with some gut issues might be a big issue. So addressing those things should have a pretty large impact on retaining CO2.
Definitely. What are some resources that you would offer people to kind of find more about some of this information?
Yeah, so I guess I'm a little biased toward my podcast and articles I've got.
I know your podcast is great, so slip it in there for sure. I recommend everybody listening to this go check out his podcast. It's great.
Well, thanks, Jayton. I appreciate that. We've got a few episodes on blood sugar, a few episodes on the gut. So those would probably be good places to start. Somewhere in the beginning of like episodes 1 through 7, really dig into some of those main pieces. So those really dig into the basics of how to re-regulate your blood sugar if that's a struggle, and how to reintroduce carbs without coming across those issues. And then the same thing with the gut. How do you bring in carbs without having all these gut problems, which are really common for people who are coming from low carb, which is so common nowadays, that a lot of times when we're going to low carb, it's because we have these gut issues, and then we get to avoid them by going on low carb, and it feels better. It comes at that long-term cost. And then when we go to add the carbs back in, the gut issues were just, the microbes are just hibernating and just kind of waiting for you to feed them again. So, so that could be a tricky situation. So I'd recommend those episodes for that.
Awesome. Heck yeah. Well, Jay, I really appreciate you hopping on here today. Where can people find you on social media, website, all that good stuff?
Yeah. So my podcast is the Energy Balance Podcast. I know I mentioned that earlier. My website's jayfeldmanwellness.com. Instagram is JF Wellness, the letters JF. And you can find me in all those places. I'm on Facebook too, and trying to post a little more everywhere on social media, but sometimes it's tough to keep up with everything. But and if another place where I think might be good for people who are looking for some real practical tips, I have a free energy balance mini course. It's like a 7-day mini course. And so you can sign up for that at jayfeldmanwellness.com/energy.
Heck yeah. Awesome. Well, thanks again for hopping on, and I look forward to having you on again soon.
Yeah, Jayton, thanks for having me. It was great.
Thanks for listening to the podcast. If you haven't already, make sure to hit the like button, subscribe, and leave a comment down below if you want us to cover a different topic.